Great. Well, thank you for all coming along today. So in terms of the National Seismic Hazard Assessment, the one that we've just released has really challenged some of the notions amongst seismologists and engineering practitioners in Australia. And I guess it's also thrown up a bunch of challenges, both from a technical, philosophical, but also a personal level as well. So I guess today what I'm planning to do is lead you through, I suppose, the development of the Seismic Hazard Assessment, why it's important, and ask the really tough questions about, are we actually preparing for the right earthquakes in our building codes, and are our communities as safe as they possibly could be? I'll jump straight into the acknowledgements, and I guess it's no surprise that this is not a solo effort. So I couldn't have done this work without the help of a fantastic team. I guess all the folks that worked specifically on the NSHA project, as well as a lot of the other GA staff that contributed. I guess in particular Grant Butler and Dave Lazinski, who were at the end of all of our requests for more CPU time on the NCI, and I guess their responsiveness to those requests. So there's a bunch of people that I need to thank. In addition, there's the Global Earthquake Model Foundation, who are responsible for developing the software that we've actually used today. And those of you who came to see the BGS CEO, David Luton, he will have already talked about the Global Earthquake Model Foundation as well, and I guess the importance that it's proposing to the work that they're doing at the BGS as well. The NCI, no surprises there. We couldn't have done this work without the NCI. And also, thanks goes out to the Australian earthquake engineering community as well. So in terms of the talk outline, I'll talk a bit about the NSHA, what is it, who uses it, and the NSHA itself is a probabilistic seismic hazard assessment or analysis, and I'll go into some of the background as to what a PSHA actually is. I'll talk about the history of seismic hazard assessments in Australia, and then specifically look at the NSHA. And that involves the community engagement that we did across the Australian earthquake engineering and seismology communities, talk about the key ingredients, and then look at some of the key outputs from the hazard map. And then asking the key questions. Are we actually designing for the right earthquakes? Geoscience Australia, we monitor and assess earthquake hazards in order to inform risk mitigation and emergency management activities. And so that process really shows the strength of GA's seismic value stream, from the geophysical networks through to the alert centre, to hazards, to the risk information that we provide, all the way through to mitigation. We provide advice and information on seismic hazards to all levels of government, private industry, and the general public. And the science underpinning the calculation of seismic hazard is rapidly evolving. And so what we need to do is we need to keep pace with that evolution of the science and make sure that we're providing the best available evidence-based information possible. But the problem is the estimation of earthquake hazard is an inexact science. As our knowledge improves, our estimate of the seismic hazard should converge on the actual or real hazard, but in reality, that's never going to be known. There's always going to be some ambiguity, some uncertainty associated with the hazard associated with these rare events. And I guess finally, the NSHA improves our understanding of seismic hazard risk and its uncertainties for Australia, allowing our communities to be better prepared for these rare catastrophic events. So I guess I'll talk now a little bit about who uses the NSHA. And when I'm talking about the NSHA, I'm talking also about the derivative products that are derived both for and out of the NSHA. So I guess the core reason why GA originally got into this game was to develop seismic hazard models that go into seismic standards building codes. And so the seismic hazard information really underpins things like the earthquake design codes put out by Standards Australia. We also have societies like the Australian National Committee on Large Dams. So they are very aware and conscious of the risks that earthquakes pose to their facilities, both in large water reservoirs and also mining tailings dams as well. And then we have groups like the Australian Building Codes Board, which is actually the government regulator who is responsible for setting the standards from which Standards Australia needs to comply. But I guess as time's gone on and the information that we're providing starts to evolve, the list of end users has really expanded considerably. So I guess I mentioned before that we do provide information to government. We have a couple of strong relationships now with state governments in the Department of Fire and Emergency Services in WA. And incidentally, this time last week, I was at a community information session on the Lake Muir earthquakes in southwest WA, for which and this was co-organised by DFES and Geoscience Australia, and was there to talk about the science behind earthquakes and the possible risks that their community might face. Additionally, we have the Queensland Fire and Emergency Services as well, in addition to a couple of other state agencies. Another big user of the hazard information is in the engineering sector. And again, these are largely for dam-related projects, so both water reservoirs and mine tailings dams. Then we get into the catastrophe risk modelling side of things. So these are essentially model vendors that provide an assessment of the earthquake risk across on a national scale, and this information is largely provided for the insurance sector. So the difference there's a lot of synergies between these two groups. Intertwined with the insurance sector, we have the reinsurers, we also have the insurance brokers, we have the actuaries that define the risk. And so overall, this group of stakeholders or end users are really probably the biggest users of the information that we put out. And they really are demanding the best available evidence-based science. And just to highlight this point, so this is a quote from the Australian Actuaries Institute, which is relatively recent in 2016. Now, you may remember the Sydney hailstorm of 1999, which still remains our most costly natural disaster. But the quote here says that whilst infrequent, earthquakes in Australia are thought to produce the most substantial costs at current time. So in terms of the people who define what the risk is, the actuaries, they're saying that earthquakes still pose the most significant threat to communities across Australia. And this is an older study now, which was the original data was compiled in 2007. But it essentially shows the amount of reinsurance cover. So reinsurance cover is the cover that our insurers purchase in case of these rare catastrophic events that even if they were to occur, they wouldn't be able to fund the capital. So in terms of global perils that reinsurance is bought for, we have US hurricane leading, California earthquake, Japan earthquake. Those are probably no surprise. The next major peril is UK windstorm, and fifth is actually Australia earthquake. Now, given property prices have ballooned significantly since these studies were done, those numbers may go up now, but that really speaks to the way that we insure our buildings in Australia. So unlike most places across the world, insurance is automatically provided in most home premiums. And as a consequence, that's why the insurance sector actually sees Australia as a fairly big risk in terms of potential losses. What is probabilistic seismic hazard analysis? So the PSHA defines the level of earthquake ground shaking at a given location that has a likelihood of being exceeded within a given period of time. So in the Australian Earthquake Loading Standards, which is the AS 1170.4, this is defined as a 10% chance of exceedance in 50 years, or is often simplified to a 1 in 500 year annual exceedance probability. So that's essentially saying that in a 50-year period, you've got a 10% chance of exceeding the mapped ground motion value within your hazard map. So this 1 in 500 year exceedance probability is actually defined in the National Construction Code, which, as you might remember, is led by the Australian Building Codes Board. So the PSHA considers all possible earthquakes that have a given likelihood of affecting a given site within the investigation period. And that time period is usually defined as the typical lifetime of a building. So that's where the 50 years typically comes from. The method is not intended to express zero risk, and it's inevitable that strong ground shaking will occur where the mapped hazard is low. And by definition, this should occur at a rate of about 10% exceedance in 50 years. And to put that into perspective, that's essentially saying that in a 50-year period, we should expect an area of Australia the size of New South Wales to experience earthquake ground shaking above the mapped hazard value. Now, I guess the question that I put to you is that an acceptable level of risk that we want to have as a society? Now, let's put Australian earthquake hazard into the global context. So this is an older study now, which was conducted from the mid-1990s to the late 1990s, published in 1999, which is the Global Seismic Hazard Assessment project. And it was really the first compilation of global seismic hazard across the world. Now, I probably don't need to point out Australia sitting there, and it's defined by moderate seismic hazard, kind of in the greens to yellows there. Now, Australia is a stable continental region, which means that typically the seismic hazard should be lower than more active regions such as New Zealand, California, Japan, and other more hazardous regions. Now, if we compare Australia to other major stable continental regions around the world, we see that our hazard is significantly higher based on this assessment. Now, I guess the question I pose is the earthquake hazard in Australia really that unique? Is our hazard much higher than most of the other tectonically stable regions around the world? So incidentally, the Global Earthquake Model Foundation will be releasing an updated global seismic hazard assessment later today. So this is the first assessment that's been updated since this 1999 assessment. And I actually highlight this because the map that was contributed to the GSHAP program still actually underpins our National Building Code today. Okay, so now for a lesson in the dark arts. How do we do a probabilistic seismic hazard assessment? So there are three main steps. First, we need to define our earthquake sources. We have our ground motion, so how do we forecast the ground shaking level for a given earthquake for an earthquake of a given magnitude at a given distance away from that earthquake, and then we construct what is our hazard curve or our hazard map. Unfortunately, the geographic representation here is still based from when I was working in Canada, so I apologise for that, for not having a local example. But say we had a site here where we wanted to build this building. We might have a fault that is somewhere near that site. Now, let's say, for instance, that the slip rate on that fault is around about 50 millimetres per year, which is possible in Western Canada, not so possible in Australia. So typically, the slip rates on our fastest moving faults are probably around 500 to 1,000 times less than some of the more active faults around the world. Now, in a seismic hazard assessment, we can represent the occurrence of those earthquakes in different ways. So what we're seeing here are what we call magnitude frequency distributions. So we have the cumulative rate of earthquakes of a given magnitude here. So let's say that this fault has a characteristic magnitude of magnitude 7.75 and a maximum magnitude of magnitude 8. So assuming that this earthquake ruptures in a characteristic style, which is this red curve here, it essentially means that most of the slip from this fault is released in very large earthquakes. So we have a higher proportion of large earthquakes relative to our small earthquakes. Alternatively, we have what's known as a standard Gutenberg-Richter magnitude frequency distribution, which essentially says that we have fewer larger earthquakes, but more lower magnitude earthquakes. And in terms of how the slip is actually distributed over that magnitude range, is that for the characteristic earthquake model, we see that most of the slip is actually taken up with these very large earthquakes, And very little of it is taken up with the smaller magnitude earthquakes because the return period of those earthquakes is not as high. Whereas if we use a Gutenberg-Richter style model, that slip is more evenly distributed across the magnitude range. But what if we don't know where there are active faults? So in those cases, we use what's known as area sources. Now, these area sources are effectively areas where we don't know whether there's any active faults, but the earthquake distribution is generally uniform over that given area. So again, we can draw a Gutenberg-Richter magnitude frequency distribution. We may have some uncertainty about the rate of earthquakes occurring in that area. So there may be fewer earthquakes, there may be more earthquakes. And we can actually put that into a probabilistic assessment by weighting our degree of belief on which model is actually the best. Now, in terms of how we get that information, so information on faults is largely derived from paleoseismology, geodesy and geodynamics type studies, whereas information on our distributed earthquake sources usually comes from earthquake catalogues. And again, that's demonstrating the importance of keeping a high quality earthquake catalogue. Okay, the second important ingredient are ground motion models. So the ground motion models estimate the expected median ground shaking intensity for a given magnitude earthquake. So we have our shaking intensity on the y-axis and distance on the x-axis. And they calculate the ground shaking intensities in terms of peak ground acceleration, peak ground velocity, and various spectral acceleration ordinates, which I'll talk a little bit about in the next slide. So the ground shaking from these from earthquakes typically depends on the magnitude, the source to site distance, the site condition, so whether you're sitting on rock or whether you're sitting on soil, the mechanism of the earthquake, so whether it's strike slip, thrust, normal, or whether you're sitting on the hanging wall or the footwall of the fault. And it's quite typical, so we have our median model here, but it's actually quite typical to have a very large distribution of our recorded ground motions. So it's not uncommon to have factors of 3 to 4 or perhaps even 5 difference in our observations from our median ground motion model. And just to highlight that, this is just an example from the 2012 Maui earthquake, which was a magnitude 5 earthquake. It's one of the better recorded earthquakes in Australia, just showing the variability in the near source ground motion in particular. And this is for a spectral acceleration of 0.2 seconds. And the model is, and the data is compared to a number of different attenuation models. Engineers typically don't want the raw recorded earthquake ground motion. So what they want is something that tells them how a building's actually going to respond. So in that case, we develop response spectra. So essentially buildings can be thought of or represented by a single degree of freedom damped oscillators. So if we look at the pictures here, so we have a relatively low-rise building, and it can be characterised by an oscillator with a natural period of around about 0.2 seconds, so high frequency, short period. We go to more of a moderate sized building, and this can be characterised with a natural period of 0.5 seconds. And then as we go to progressively larger and larger buildings, we go to progressively longer and longer oscillation periods. Now, for each of these models, we have an input, or oscillators I should say, we have an input ground motion. That causes this oscillator to move. And what comes out the other end is this response of the oscillator. And so what we do is for each of the periods, we pick off that maximum value and we develop a response spectrum. And so the response, and so this is highlighting this value here, 0.2 seconds, 0.5 seconds, and 1 second. And we do this for the range of vibration periods or oscillation periods and generate our response spectrum for a particular ground motion observation. So now we're getting to the final step in terms of constructing a hazard curve. So say, for example, and this is a very simplified case, that we have our site here. We have two earthquake sources, a fault that could produce a magnitude 5.5 earthquake that has a return period of 10 years, and another fault at 50 kilometres distance that can produce a magnitude 7.5 earthquake with a return period of 200 years. So let's focus on source A for now. Because it can produce a magnitude 5.5 earthquake, what we're showing here is essentially the ground motion model for a magnitude 5.5 with a spectral response of 1 second. And we have our median model here, which has a probability of exceedance of 0.5. And then we have some uncertainty bounds around that median model. So a probability of exceedance of 0.16 for the higher model and 0.84 for the lower model. We look at those values at 10 kilometres, and so, for example, for a magnitude 5.5 at 10 kilometres, the probability of exceeding 0.088 G is 0.16. So we can then calculate what's called a frequency of exceedance. So we know that this earthquake occurs once every 10 years, so the frequency of, the chance of that earthquake occurring is 0.1. We multiply that by the probability of it exceeding this value, and so we get our frequency of exceedance of 0.016. In terms of developing our hazard curve, what we do is then calculate this frequency of exceedance. We plot the spectral value here with the frequency of exceedance, and we do this for all possible ground motions from source A to make a hazard curve for source A. We do the same thing for source B and then combine them to come up with our total hazard curve. Now, to pick a value for our hazard map, what we do is we look at the desired frequency of exceedance, and in this case it's for a 2475-year return period ground motion. We see where at this frequency of exceedance it intersects this hazard curve, and we map this level of ground shaking. So this is just for one site and one ground motion model. In the NSHA, we've used multiple ground motion models, roughly 55,000 points or sites, and rather than just 2 earthquakes, we're simulating thousands of earthquakes for any one site in the NSHA. And we're also doing it for multiple periods, so we're doing it for 10 spectral periods in addition to peak ground acceleration. So you can quickly see how the numbers of calculations mount pretty quickly. Why do we want to update now? So the last assessment was completed in 2012, and most national hazard maps are updated on a 5 to 6 year period or cycle. The US has actually now moved to a 3-year cycle for theirs, and that's actually to mitigate some of the major changes or swings in seismic hazard estimates, because they were seeing that the science advanced so much in a 6-year period that the hazard values changed considerably. And so what they wanted to do by implementing a 3-year cycle was try and damp, I guess, some of those major changes. As I mentioned, there's been significant advances in earthquake science since that time, and not updating the model using this science diminishes the credibility of the model itself. Private industry needs to ensure that future investments are based on the best available and evidence-based information. And I guess this is probably my personal opinion, that the hazard models based on 1980 science, such as what's in the current AS 1170.4, don't really offer this level of credibility or confidence. And so I guess the NSHA itself was originally being prepared for the inclusion into the Standards Australia 2018 update of the earthquake design actions. Okay, so now for some history. So the first earthquake zoning map was produced, and this is largely produced after the Meckering earthquake, which we've just had the 50th, or commemorated the 50th anniversary for. But it took some time to actually get the building codes implemented. And so the first standard was finalised in 1979, and the earthquake zoning map that went into that was produced by Denham and McEwen. The first probabilistic seismic hazard assessment was undertaken by Gall, Michael Lieber and Rinn, and so that was published in 1990. And this was really a huge advance for earthquake hazard assessment in Australia. In terms of the ground motion models that they used, they developed their own models based on modified Mercalli intensities. So these are qualitative assessments of earthquake ground shaking based on the effects on people and buildings. essentially. So they're not instrumental measurements, but they can be converted to instrumental measures, such as peak ground acceleration and velocity, using conversion equations. In 1991, McHugh and others updated the Gall map and produced this seismic hazard assessment, which now underpins the AS 1170.4. And so it was first implemented into the standard in 1993, and this was largely in response to the 1989 Newcastle earthquake. So a couple of key differences between this map and the Gall map is that, for one, that the Tennant Creek earthquakes occurred after the Gall map was finalised, so now we see a large bullseye here where the Tennant Creek earthquakes were, but also the Newcastle earthquake occurred after the map was finalised. Now, this map isn't actually a probabilistic seismic hazard assessment. They used the contours of Gall and adjusted them based on their collective knowledge and experience of earthquake occurrence in Australia. In terms of some more recent history, in 2012 we made an attempt to update the hazard map that goes into the building code. This used modern PSHA software, included multiple seismic source models, modern ground motion models, and applied some corrections to the earthquake catalogue. Unfortunately, this model was rejected due to a lack of consensus amongst the Australian seismologists. And the large concern amongst the seismologists were that they weren't really included in the process. And so because of that, the model was rejected from being included in the standard. So this time around, what we really tried to do was to seek that broader community engagement. So the NSHA process was initiated to ensure a wide consultation among our major stakeholders, and that includes seismologists, engineers, and our other end users as well. And so some of the methods for harnessing that community support. This time around, we made a call for third-party models. So that meant that the Australian seismological community could contribute their own models to the earthquake hazard assessment. We also held various workshops and special sessions at conferences, such as the special session at the 2016 Australian Earthquake Engineering Society conference. We also held expert elicitation workshops, and this single dot point doesn't really do the elicitation process any justice. So this is a process where we brought together the key players in seismic hazard assessment in Australia, as well as some of the end users as well, such as the engineers. And what we did is we looked at all of the various candidate models that had been submitted to the seismic hazard assessment or for inclusion to the NSHA, and we essentially weighted the models going into that through the expert elicitation process. Now, each expert was allowed to provide their own weights for the particular models, but what we did differently is that before the workshop started, we asked a bunch of seed questions. So the seed questions were questions that had known quantitative answers, but no normal person would be able to actually get the right answer. So what it was really trying to assess was what the confidence of the experts' understanding of the topic subject matter was. And so that information was then used to actually weight the responses of each of the experts. So it was a really interesting process. In addition, what we did is we also established a science advisory panel. So that included key members of international agencies, such as from the USGS, from Indonesia, from GNS Science in New Zealand. And so they provided, I guess, a watching eye over the work that we were doing for the NSHA. So as I've already mentioned, the key reason for developing the NSHA was to try and get it into the next update of the Australian standard. A couple of the key advances in the NSHA included the consistent expression of earthquake magnitudes in moment magnitude, and I'll talk a lot more about that shortly. The inclusion of uncertainty through the use of multiple third-party models, and I guess one of the important advances this time around was really the inclusion of the National Fault Source Model using the Neotectonics Fault Database. Okay, so a spoiler alert. This is the new seismic hazard assessment, and so it's tied to a particular ground condition, and so what it's showing is the peak ground acceleration with an exceedance probability of 10% in 50 years. In terms of some of the key aspects of the map, so what we're showing is relatively high hazard in places like the southwest seismic zone, which is pretty consistent with the previous maps or previous assessments. And so this is a region where we've had historically some very large earthquakes, such as the Meckering, Kalingari and Kadoo earthquakes. Another key area that's really lit up is the East Gippsland area or Latrobe Valley area. And so the reason behind that is largely because of both the historical earthquake occurrence, but also the inclusion of the active faults. So we know that there's high density of faults in that area. And then some of you might have read in the newspaper or Canberra Times that Canberra is actually now the capital city with the highest earthquake hazard in Australia. And that's largely due to the inclusion of the National Fault Source Model. I guess the kicker there is that relative to the hazard map in the AS 1170, the numbers that we're coming out with are on average 72% lower than what's in the current building code. And so the standards subcommittee were pretty concerned by that drop in the earthquake hazard. And it effectively means that given the low hazard that we're now forecasting, essentially designers will no longer have to design for earthquake. And I don't think anyone on the committee necessarily wanted that to happen. I guess what's really required now is to have a fundamental rethink about how we define earthquake hazard and how it's used in our codes. Okay, so just for some background here, I'm going to be talking about various neotectonic domains. We're essentially defining everything that's east of the Tasman line as non-cratonic Australia. Everything that's west of that line is cratonic Australia. And then we have our extended continental margins here as well. You saw this map in my opening slide, but it's really showing the historical distribution of Australian earthquakes. So we have high clusters of earthquakes here in the Southern Highlands, quite a high density of earthquakes also in the Flinders and Mount Lofty ranges, and then high occurrence of high rates of earthquakes in the southwest seismic zone as well. And we also do see a significant amount of activity up here off the northwest shelf. So in terms of the key ingredients of the NSHA, I'll talk a bit about the earthquake catalogues, the sources that go into it and the ground motion models. The catalogue itself really required a fair bit of work. So we took essentially a third-party catalogue which had already ingested all of GA's earthquake solutions, but had improved some of the locations of earthquakes, particularly in eastern Australia. So that was used as the basis for our earthquake locations. And importantly, relative to the 1991 map, it's included roughly 3 decades worth of additional data. We went through a process of revising those local magnitudes due to the use of inappropriate attenuation formula, and I'll talk about that shortly. Additionally, we developed conversion equations. So what we need to do in PSHA is we need to use an earthquake magnitude scale known as moment magnitude. Also importantly, the methodology that we're using applies an Australian-specific declustering algorithm. So what we have to do in a PSHA process is we assume that it's a Poissonian process, in that earthquakes occur both temporally and spatially independently. So this process essentially removes dependent events. And we also develop new magnitude completeness models as well. Why are earthquake catalogues important? So effectively the PSHA process assumes that past seismicity is representative of future earthquake hazard. And so magnitude frequency distributions allow us to forecast the rates of earthquakes that will occur in the future. And so we usually use a formula similar to this, which is a standard Gutenberg-Richter magnitude frequency law. And so this is essentially what it looks like with real data now. So this is for an earthquake source in the Flinders Ranges, and we see the earthquake magnitudes and the cumulative rate of occurrence here. And so the B value, which is commonly referred to, essentially relates the occurrence of small to large earthquakes. So having a high B value means that you have relatively more small earthquakes relative to your large earthquakes, and a low B value is you have relatively more large earthquakes. And again, this really demonstrates the importance of having accurate earthquake catalogues, which is possible through our geophysical networks and the Alert Centre. So historically, most of the earthquake magnitudes in our catalogue are what we define as local magnitudes, which are very similar to the Richter magnitude. So that was a magnitude scale originally defined in 1935 to define the relative size of earthquakes in Southern California. And it's commonly known as the Richter scale, which you're probably aware of. It's generally observed that the scale is not able to estimate accurate earthquake magnitudes for very large and also very distant earthquakes. So the scale tended to saturate around about magnitude 6. All other magnitude scales, or types of magnitude, such as body wave magnitude, surface wave magnitude, moment magnitude, are calibrated to Richter's original definition to some extent. However, even though the original Richter equation was defined for California, there has been the development of some local magnitude scales developed specifically for Australia, and these take into account local ground motion attenuation properties. So this is a plot just showing a comparison of earthquake magnitudes calculated using a Californian earthquake magnitude scale and the Michael-Lieber-Malenfant equation, which was produced here in Australia in 1992. Generally what it shows is that, and this is now plotting the difference in magnitude between the Michael-Lieber and the Californian equation, and plotted against the Michael-Lieber magnitude here. And so for smaller earthquakes, we generally don't see a major difference between the earthquake magnitudes, but we do tend to see a much larger difference at larger magnitudes, by up to 0.4, 0.5 magnitude units. And that's because of the different attenuation assumptions that are assumed between the Californian and the Australian magnitude scales. So once we recognised this, we really had to go to the effort of correcting our local magnitudes in our catalogue, because many of the, say, pre-1990s earthquakes still use the original Richter magnitude definition. So at regional distance, or at distances from about 50 to 180 kilometres, the Australian magnitude scales or formulas are pretty consistent with the original Richter formulation. But it's really at those larger regional distance where they tend to diverge. And so these plots here are now showing for different magnitude scales. So this is the Richter equation, this is the Bakken and Joyner, which is another Californian equation here. And then we have a couple of Australian equations, which is the Michael-Lieber and also the Wilkie equation, which was calibrated based on some fairly limited data at the time. So, and the plots are showing what is the station magnitude recorded at a given hypercentral distance minus the mean earthquake magnitude. So it's essentially the residual for each individual observation for each individual station. The important thing is that earthquake magnitude, by definition, is independent of distance, and we clearly don't see that if we use our Californian equations. In contrast, if we use an Australian equation, and this is the equation that's used in our current Alert Centre, we see generally little bias with distance. So we went through a process of correcting the catalogue, and I won't go through the details of that, but I really find this plot quite powerful. So this shaded area here is around about the time period between 1986 to 1992 where Australian-specific magnitude scales were developed. These bars here represent the number of earthquakes per year that exceed magnitude 4.5 across Australia. And these dashed blue bars are essentially the average annual number of those events. And I've separated that out in essentially two 30-year periods, before 1990 and after 1990. So typically what we're seeing before 1990 is that from an unmodified catalogue, we typically should expect around about 6 magnitude 4.5 earthquakes per year. Whereas after 1990, which is when these equations were developed and implemented, we typically see that there's probably around about 3 of these earthquakes exceeding magnitude 4.5 per year. There are a couple of possible explanations for this. One is that we really did have much higher earthquake occurrence rates prior to 1990, or the second one is that we were just overestimating our earthquake magnitudes. So these dashed orange lines are essentially now what is in the corrected catalogue. Because all modern ground motion models are now typically calibrated to the moment magnitude scale, it's essential that earthquakes in our catalogue are also calibrated to this scale. And so the reason why the moment magnitude scale is used is because it doesn't saturate with magnitude, and it's typically constant across the range of various magnitudes. And it's typically also best global practice. Unfortunately, moment magnitude is typically not defined for Australian earthquakes. But using a reference data set of roughly 240 events, we were able to essentially develop what is a conversion between our local magnitudes and our moment magnitudes here. So what we see is roughly a polynomial or bilinear relationship between our local magnitudes and our moment magnitudes. Comparing that with some more recent global studies, and this is a study from Japan. It's not quite the same magnitude type, but it's a similar amplitude-based magnitude. They see very similar relationship to what we're showing here for the Australian data set. So the combined effects of our magnitude adjustments, what we're seeing is that the rates of large to moderate earthquakes have approximately halved relative to the original earthquake catalogue magnitudes. This also means that the B values have increased due to the conversion of the ML to MW, which again decreases the rates of our large earthquakes. So these plots here are showing the cumulative number of earthquakes for magnitudes 4.5 and greater and 5 and greater. And we're seeing the red curve is the original magnitudes, the green curve is for the modified local magnitudes, and the blue is for the moment magnitudes. And so comparing the red to the blue, for magnitude 4.5 and greater, we're seeing roughly half the number of earthquakes. And that difference gets even bigger as we go to larger earthquakes. So how do these magnitude adjustments affect the hazard? Effectively, what this means is that we're really reducing the occurrence of our large earthquakes. And that has a fairly significant on the earthquake hazard. So this plot is showing essentially that the hazard that would be calculated from the original earthquake, if we used a catalogue of original earthquake magnitudes, and we've divided that by hazard that is calculated using our modified catalogue. And generally what we're seeing is a reduction pretty much all the way across Australia of factors 2 or more. So moving on to the earthquake sources now. In the NSHA, where this is probably the global model now that has incorporated the most number of different seismic sources of any other global model. And I know that when the Global Earthquake Model Foundation were trying to implement our model, it was creating some severe headaches for them because they weren't actually used to calculating something quite so complex. So what this allows us to do is it really allows us to explore the epistemic or modelling uncertainty associated with modelling seismic sources. So these seismic sources can be classified in different ways. So we have our background seismic sources, the regional seismic sources, and smooth seismicity sources, as well as our seismotectonic models, which is essentially the regional models that have the neotectonic faults added to them. This is just a table of all the different models that we used within the NSHA in their various classes, and then we have these other weights that were derived from the expert elicitation workshop. So in terms of the area-based models, why do we want to use both background and regional seismic source models? So the background models are typically those that are defined with 15 area sources or fewer. The rationale behind that is that the recent seismicity may not necessarily be predictive of future earthquake activity. The historically surface rupturing earthquakes seem to have occurred where there have not been previously mapped faults. What we're potentially seeing is that these earthquakes are occurring randomly in space. And essentially what the background model allows us to do is to account for earthquakes to occur anywhere with an equal probability. So in contrast, the regional source models, they typically tend to have more area sources associated with them, which is saying that the spatial distribution of historical earthquakes is going to be non-uniform across large areas of the country. It's also saying that the distribution of the historical seismicity may be a predictor of future earthquake activity. So this is a map just showing the difference between some of the contributed models. So we have our background models over here and some of the regional models on this side. And we can generally see that the background models are defined by these very broad area sources, and the regional area sources, particularly for the AUS6 model, are very detailed in some areas. So in terms of what that then looks like for differences in earthquake hazards, so we've taken each of those independent models, calculated the seismic hazard associated with them, and we see very different patterns in the earthquake hazard associated with each of these independent models. I guess for this one, for example, what it's doing is it's really smoothing the earthquake occurrence rates all across very large areas across the country. Whereas for this model in particular, what it's doing is it's really focusing the historical earthquake activity in specific zones. An additional model that we're using are smooth seismicity models. So these are really data-driven models that don't rely on an analyst's interpretation of seismic source zone boundaries. So previous models, they required an analyst to sit there and actually physically draw those source boundaries. And again, it assumes that the past seismicity will be representative of future seismicity. So we had 4 of these models contributed to the NSHA. Each of them has varying degrees of smoothing associated with them. Additionally, what we've done is we've recognised that seismic hazard from our northern plate margin is actually a fairly big contributor to the seismic hazard in northern Australia. To put that in perspective, we've just received 800 felt reports in Darwin from a recent earthquake in the Banda Sea. And so what we're attempting to do here is we're developing seismic source models that can be stitched to our local models and to account for the potential ground motion hazard that we see from these large earthquakes that occur off our mainland coast. We didn't reinvent the wheel here, so what we did is we essentially adapted the seismic source models from a variety of different studies. So we took the recent Indonesian seismic hazard assessment, the relevant parts of that. We also augmented that with the Papua New Guinea seismic hazard assessment conducted in 2014, in addition to some of the information developed for the global probabilistic tsunami hazard assessment by Gareth and others. We also include both area and fault source models for this model and stitched a single model to essentially every earthquake source model that was developed for Australia. Additionally, we've used the National Fault Source Model, and this is just a map showing the various fault sources in southeastern Australia, colour-coded by their relative slip rates. I'm sure you all know the Lake George Fault, but essentially Canberra here is bounded by 2 of Australia's fastest moving faults, the Lake George Fault and the Murrumbidgee Fault here to the west. Another idea that Dan's been talking about recently is the possibility of one-off ruptures in cratonic domains. So these are domains that are essentially west of the Tasman line. So historically we've seen a number of surface rupturing earthquakes in these areas, but paleoseismic studies on these have suggested that there haven't really been any previous earthquake ruptures associated with them. So it's really starting to rethink this notion of earthquake recurrence, and is it really meaningful in cratonic domains? So we know in these domains that erosion rates are typically pretty low, but we don't see significant topographic relief built by these faults. So essentially what that's saying is that the erosion rates must be greater than the earthquake uplift rates. So are these earthquakes that we really need to consider for our long-term earthquake forecasts? And finally, moving on to the ground motion models. So these are some of one of the components that incorporates the largest uncertainty in our seismic hazard assessments. The models that were used for the 1991 assessment, which is still in the AS 1170 code, essentially those that were derived by Gall and others in 1990. The modern models that we've actually used for the hazard assessment are these coloured ones. The original ones developed by Gall and others are these solid black line ones here, and these were actually adjusted for the 1991 hazard maps because there was a belief at the time that the Gall model actually underestimated the peak ground accelerations that we could experience from Australian earthquakes. So they are adjusted and actually increased. So these dotted black lines here are essentially the models that were used in the AS 1170.4 hazard maps. We can see, particularly for non-cratonic models, that the modern models are predicting much lower ground motions than were used to inform the 1991 maps that are in the AS 1170.4. Cratonic models are not as different, but we do see that the rates of attenuation as we go out to longer distances are much slower for the older models as well. Now, similar to the comparison with the catalogue, this map is showing essentially the ratio of the seismic hazard that's calculated using the older ground motion models, the Gall models, divided by the hazard calculated using the current suite of ground motion models that were used in the NSHA. And we can see considerable drop in ground motion hazard, particularly in Eastern Australia. And that's largely because of the large differences between these models here. So we're seeing differences of factors of 4 or more in large parts of Eastern Australia. Some of the key highlights for the NSHA, we've updated the earthquake catalogue and it's been uniformly expressed in terms of moment magnitude. We've used 19 seismic source models, both GA and third-party contributors as well, and all of those models were weighted in some way through the expert elicitation process. We've used multiple modern ground motion attenuation models, and I guess that the NCI has really facilitated our ability to generate or calculate the seismic hazard across the country. In terms of some of the products, we're not just calculating hazard for peak ground acceleration as is required by the building code. We're doing it for another 10 spectral periods. This is just an example as 0.2 and 1 second. The interesting part about the longer period ground motions is that we start to see pretty significant influences from our offshore earthquake sources as the ground motions propagate through the crust between the Timor Trough and Northern Australia. In terms of some of the products, we're planning to release 7 GA records. 5 of them are already out. Overarching model overview is currently in review, so thanks to Phil and Gareth for offering to review that for me. There's an individual report on the expert elicitation, which is an interesting process in itself, so I recommend you take a look at that. Ground motion model selection and ranking, 1 specifically on the earthquake catalogue, 1 on the plate margin sources, 1 that's still in preparation for the input files, and another one that has a complete suite of the output data package. And I guess importantly, all of the data is currently hosted on a public GitHub repository, and it's intended to be transparent and repeatable. So I guess that's the main thing. Now, if we go back to the original GSHAP or the AS 1170.4 map and do a direct comparison, pretty difficult to compare in this colour palette. So what I've done is I've converted it to the same colour palette. So now you can start to see why the insurance sector is actually pretty interested in the results that we're coming out with, because what we're seeing is that the maps that were produced back in the 1990s were really pretty conservative estimate of the seismic hazard across Australia. And so this comes back to the question, are we really designing for the right earthquakes? So again, the seismic hazard that is calculates as a given ground motion level on engineering rock that has a given probability of being exceeded within a given time period. So that's typically taken as a 10% chance of exceedance in 50 years in the building code. That said, we shouldn't be surprised if at any location we observe accelerations exceeding the mapped value. I guess the question that I have posed to me quite often is that a failure of the PSHA methodology, and that really any exceedance is a failure of the method. I guess my response to that is that we can minimise those exceedances, minimise the earthquake risk, if we actually design for lower probability or rarer earthquake ground motions. And so just to follow the example of some modern codes in developed countries that have similar tectonic environments, such as the US and Canada, they're actually now designing for a 2% chance in 50-year exceedance. Essentially rarer earthquakes contributing to the seismic hazard and the earthquake design provisions. And the reason they did that was really because they recognised that there was currently inequitable risk on a national scale, and fundamentally to account for those rare black swan events that we know can occur in our stable continental regions. This plot here is also interesting, and it's what's known as the KP factor, or the probability factor, in our building codes, and it effectively scales our 1 in 500 year hazard to different probabilities of exceedance or different return periods. So this dashed line is essentially what's in the building code, and that's taken directly from the New Zealand code. So it's for an active tectonic region. We see the curve for Darwin is actually pretty similar to that, and that's because it is affected by these more common large earthquakes. But when we look at our typically stable continental region sites, we see that our scaling quickly increases. So we go to higher hazard very quickly as we go to longer return periods. So that's part of the rationale why we should really be thinking about moving to lower probability, longer return period ground motions for defining our building codes. So this is my final slide now. So what is the challenge ahead? It's pretty clear that the modern estimates of 10% and 50-year seismic hazard are significantly lower than the 1991 era AS 1170.4 values. The question is, do these values really offer us enough seismic protection? And I don't think anyone involved in the building code really thinks that we should be going to these seismic hazard values. It essentially will mean undoing the good work that has been done in the earthquake engineering community over the last 30 years. The new code has maintained the 1991 map, but has implemented a 0.08 G hazard floor. I guess it's already a conservative map, but they've made it even more conservative. And I guess moving ahead, should we consider moving to a 2% and 50-year probability level? And so there's a range of advantages to this. So it allows greater protection from these rare black swan events. It'll bring Australia into line with modern codes in similar tectonic environments such as the US and Canada. And I guess importantly, the NSHA 2% and 50-year maps are really suggesting that there are some key sites that we're designing for using our current code that may actually be non-conservative, and those are places like Adelaide, Canberra and Morwell in the Latrobe Valley. Unfortunately, this really can't be achieved without substantial change to the overarching National Construction Code that defines the probability of these events the probability in the earthquake building code. So it's probably going to take years of lobbying and advocacy with the Australian Building Codes Board in terms of getting this change through. In the meantime, we see that there really is a continued demand for this modern evidence-based seismic hazard information, and that's really demonstrated by the demand for these products from our end users. And thanks for your patience, and I guess I would like to wrap it up there.